Welcome back to our ongoing discussion on surface chemistry. This is our fifth meeting on this topic. We will start off by first recapitulating what we discussed in the last meeting. In our last meeting, we talked about the importance of the pre-exponential factor and the energy of activation for the catalyzed reaction. That is, EA cat is less than EA uncat. So, in this expression that you have got, you compare this, the K cat versus the K uncatalyzed, and what we showed was that the activation energy for the catalyzed reaction is lower than that of the uncatalyzed reaction, but the pre-exponential factor of the catalyzed reaction is also lower than the A uncatalyzed. So, this decrease in EA cat is somewhat offset by this decrease in A cat, as a result of which K cat is not as big as it would have been had these two been the same. So, that is something, and we looked at this. If you plotted log K versus 1 over T, you had the uncatalyzed reaction, which had a large slope and a high intercept, and the catalyzed reaction, which had a smaller slope and a smaller intercept. So, that is one thing that we discussed. The other things that we discussed were the aluminosilicate based zeolite catalysts, where we said that this is made up of silica and alumina tetrahedra, and there are both Lewis and Bronsted acid sites in these zeolite cages, which helps its catalytic properties. And the last thing that we considered was enzyme catalysis. And we talked about how efficient enzymes are in catalyzing reactions. That you can do it in water, but unfortunately the temperature range over which you can use enzyme for catalyzing reactions is limited. So, is there a limit on the pH range over which enzyme catalysts work, and most importantly they denature, which means that if you raise the temperature or change the pH, they denature, and there is only a limited set of reactions for which enzyme catalysis works. So, with this recapitulation of what we discussed in the last class, we will now move on to something else, which is the last portion in this unit that we have got. So, let us start off by asking this question: what is common about smoke, homogenized milk, and shampoo? So, the question is, what is common amongst these three things? This is the question before us. Is there anything, smoke, homogenized milk, something that we drink, shampoo that we use to cleanse our hair, for example, seemingly unconnected things? These three unconnected things which appear to us to be unconnected are all examples of what are called colloids. Some of them might be called emulsions, but in any case, that's something. The common feature amongst these three examples that I have listed here is that they would generally be classified as colloids. So, the question that we have got to first answer is, what is a colloid? Where did it get its name, for example? What is a colloid? To understand what is a colloid, let us go back to the first experiment that was done. The name itself is attributed to a person by the name of Thomas Graham. Who you might have encountered earlier. Thomas Graham is the same person whose name is associated with diffusion of gases. So, the same Thomas Graham was looking at diffusion of liquids in 1851. And I will illustrate what is the experiment that he did. The experiment that he did was, he took a container in which he took some solution like sodium chloride. He covered this container with animal gut. Animal gut, what it means is that it is the membrane that forms the stomach of an animal. Yeah, it sounds horrible, but that is what it is. You could instead use parchment paper or something like that. So, he takes a solution of sodium chloride, covers this container with animal gut, and if you are into racket sports, the string of your racket is typically, in the olden days, used to be strung with these animal guts, which are pulled out into strings. So, essentially this is a semi permeable membrane, and then he put this into water solution. So, here is water. So, he takes a solution of sodium chloride into this, and then he puts it into water. And a similar thing he does with other things like gelatin, tannin, and other salts like magnesium sulfate, etc., etc. And what he found was that when he did this experiment, this is called a dialysis. So, he did this dialysis experiment where he took various liquids in this container, he dipped this into water, and there is a semi-permeable membrane, animal gut, which allowed some things to go through into this water, whereas other things did not. This was in 1851, and what he found were that there were two classes, things like sodium chloride, magnesium sulfate, etc., they dialyzed quickly, which means that the concentration of the solution, the salt that was dissolved went into the water solution, and this concentration of the salt increased here. Whereas, when he considered other things like gelatin, tannin, etc., these things did not go from here into this. So, he thought there was something strange or the way the behavior of these two kinds of things, there was some difference in the way they behaved when they did this. And all the things that he considered in the first set, they had a tendency, at least in the years 1850, there was this tendency for these to crystallize. So, the class of compounds that dialyzed quickly, he called them as crystalloids. And those that did not dialyze, or those dialyzed slowly, not quickly, slowly, he called them colloids. And colloids comes from this Greek word. This one, if you know the Greek alphabet, this is kappa, omicron, lambda, lambda alpha. And if you wrote this in English, it is KOLLA. And kolla in Greek means glue. So, what he meant was that there was something about these kinds of substances which held them together, which did not allow it to go through this membrane into the water. So, there was a glue that held these kinds of compounds together, which did not allow them to go here, and that is what he considered to be colloids. So, the class of compounds that did not easily undergo dialysis, he called them colloids, and those that easily went across the membrane, he called crystalloids. It turns out now in the modern day that this classification of Thomas Graham into crystalloids and colloids is not appropriate, because you can find lots of crystals which, if appropriately made, do not undergo dialysis, and you can appropriately make those that were considered as colloids in the olden days, which you could also dialyze. But nonetheless, this is where this idea of colloids came from. The name comes from Thomas Graham in 1851. Now, the other thing that you can do is to look at what people have called about colloids. So, some people call colloidal chemistry is called by Wolfgang Ostwald Wolfgang Ostwald, by the way, is the son of a Nobel laureate Wilhelm Ostwald and worked a lot on colloids. He called colloid chemistry the world of neglected dimensions. This was in the 1900s. In those days, very few people worked on colloidal chemistry, and his book was titled The Colloidal State, the World of Neglected Dimensions. Some other people call it the chemistry of grains, drops, bubbles, filaments, and films. That is another popular definition for colloidal chemistry, and some other people call it the chemistry of everyday life. Whatever it is, whatever definition that you use, in all these cases what colloids are is essentially some kind of, it is somewhere between a solution. A solution we all know. A solution is something where we have a molecule or ion which is dissolved in some continuous medium. That is what we have as a solution. And a suspension is something where you have a compound which does not dissolve, which by mechanically mixing you put it into a continuous phase. And colloid is something that comes in between a solution and a suspension. So, colloids typically will have a dispersed phase. So, let us try and get this right. So, colloids will typically have a dispersed phase, means some material like the solute that you have in a solution, which is dispersed into a continuous or dispersion phase. And this is a very tricky business, because if you have something which is insoluble in the dispersion phase, then it very quickly will precipitate out. So, often when you put a dispersed phase into a continuous or dispersion phase, we also need something which helps the stability of the dispersed phase in this colloidal solution, and that is typically called an emulsifying agent. So, this is what holds this together. So, if you looked at any colloid, what you would have is a dispersed phase in a continuous or dispersion phase, and there are various ways of doing this. So, if you looked at this, the kinds of things that you could do is that you can have colloids of different types. So, here is the various dispersed phase, and here is the various dispersion medium that you have got, the name for this kind of colloid, and one example each in this. And you would do well by going and looking at your book to figure out other examples, because that is probably something that you would need to know. And look at what I have got here: smoke I have got here, milk I have got here. I do not have shampoo on this. So, you can see that they are different kinds of colloids. And what do we have here? You have 3 states of matter here, and you have the 3 states of matter here. And if you are thinking quickly, you are saying, I have got to have 9. I have got to have 3 possibilities of dispersed phase, 3 possibilities of dispersion medium, and you are saying that, look, I have got to have 9 of these, but you will only see 8. Why is that? You only have 8 here because 2 gases will mix in all proportions. So, I can't disperse a gas phase in a gas phase. So, instead of 9, which I expect to have 3 possibilities of dispersed phase with 3 possibilities of the dispersion medium, I cannot have the gas dispersed in gas. So, I have 8 possibilities, and these are their various names. Yes, whether you like it or not, I think it might be in good order for you to remember these names and more than one example, because that is probably something that is expected of you for your examination. So, these are the various kinds of colloids that one could have, and you have 8 different kinds, and you will see now why this is called the chemistry of everyday life. These are things that you will come across. If you live in Delhi in winter, for example, fog is a big problem. Smoke, that is something that is pollution that is affecting us. If you happen to drink soda, for example, you have gas, or any carbonated drink that you have got, that is an example here. Homogenized milk, you know, the milk that you get in packets these days, those are what are called homogenized pasteurized milk. If you take normal milk, cow's milk for example, they have different textures from the milk that you would get in the kind that you get in the plastic containers. And the reason for this is that if you let normal milk stay for some time, the fat that is present in the milk tends to have this thing of what is called creaming, where the fat will separate out from the liquid phase. To avoid this, in homogenized milk, what they do is they take milk and they put it in through high pressure and you expand it, and all the fat molecules that are there in the milk will then get dispersed into small particles which will go into the liquid phase. So, that is what you have got is a liquid emulsion that is called milk. Paints, for example, are also examples of all this. So, you have various examples, and pretty much anything that you come across is a colloid. So, there is one reason why it is called the chemistry of everyday life. The other thing that it is that many processes that you are familiar with involve colloidal phenomena, and I am not going through this list and going to read it out for you, but look at this. If you read this, you will find that pretty much anything that you have come across has something to do with colloids. So, there is great importance associated with colloidal science for everyday applications, as well as things that are useful in the industry. So, this is more than one reason that we need to study colloids, and I have here once again listed some of the colloids that are used commonly here. You see aerosols, for example, that you have in these cans that you have got, cement, cosmetics, pretty much a lot of the things that you come across on a day-to-day basis are colloids. So, what we will do in the next few minutes is to look at some of the properties that differentiate colloids from normal classical chemistry. So, here I have listed the difference between colloidal state, and note that it is not a colloidal substance. Any substance could behave as a colloid. So, rather than call it colloidal substance, we call it the colloidal dispersion or the colloidal state, and here I have compared classical chemistry with colloids that you have got. So, typically in classical chemistry, the particles that are involved are limited size, by which I mean that the molecular weights that we are looking at is reasonably small, maybe 600, 1000 Daltons for example. So, we are dealing with particles which are relatively limited in size. On the other hand, colloids typically have particle size which are much bigger, right. The other thing that you will notice is that there is a significant freezing point lowering that you see in classical chemistry, whereas it is almost undetectable in the case of colloids. And these are other things that we will come to in just a little while. And so, what I will do in the next few minutes is discuss some of the properties that are specific to colloids and interesting in its own right. So, the things that we will look at can be classified into three types. One is the optical property, the other is the kinetic property, and then its stability. These are three things that we will look at. Okay. The first thing that we will come to is the optical property. If you happen to go to a movie, a cinema, and you happen to turn back and look at the projector that is projecting your movie onto the screen, and if you looked at it, you would often find that the light that comes from the projector is seen very clearly because of the dust particles that come into the light beam that comes from the projector. And this effect is, this light being seen when you have the projector is because of dust particles scattering light. And this is something that is very, very typical of colloidal particles, and this is called the Tyndall effect. So, why does it happen with particles like this? There is something unique. So, the particles that you have in colloids are relatively big, right. So, this Tyndall effect is something which led to Zsigmondy getting the Nobel Prize for what is called ultramicroscopy. So, imagine a light wave that comes in and you have a particle here, and imagine that the wavelength of the particle is almost of the same size as the particle itself. Now, when you have a wave which comes in like this and strikes a particle, the particle will scatter light. So, some of the light goes through and this is transmitted, whereas some of the light that comes here will get scattered and will go off in arbitrary directions. Now, if the size of the particle is almost the same size as the wavelength of the light that is used, then a wave that is scattered from one side of the particle will be out of phase with the wave that is scattered by the particle at the other end. So, what happens here is, in this plane, the two waves that come from these two edges of the particle are out of phase, or they mix randomly. There is interference there. Whereas, if the particle is small compared to the wavelength, so typically people say is, if the particle is less than 20 times the wavelength of the light that is used, then you do not see this interference effect. So, when the particle size becomes large relative to the wavelength of the light, then you have tremendous amount of scattered light. And it is best to look at the scattered light at 90 degrees. So, if this is the incident light, you look at it at 90 degrees from the incident or the transmitted light. So, if you looked at the scattered light, these colloidal solutions tend to scatter a lot more light, and this is what Zsigmondy did to look at ultramicroscopy. He developed what is called ultramicroscopy. So, how it worked was that what Zsigmondy did was he took sunlight. So, imagine that sunlight comes through and he put this onto a mirror, let us say. So, he takes, this is a mirror and the light comes through, and then he took a lens here and he focused it onto a sample. So, this is a sample containing the colloid, and then he put a microscope here. So, he was essentially in this configuration. The light comes in and he is measuring light at 90 degrees to this. And one of the beauties of the colloidal solution is that they have very, very distinct color. So, if you took, for example, gold colloid, and gold colloids are very important because around the 1860s, Michael Faraday synthesized some gold colloids which are still present in England. So, you can imagine, so 1860 to 2020, so almost 150, 200 years, these gold colloids synthesized by Michael Faraday are still present in England. So, what Zsigmondy was able to do is take sunlight from here, put it through this, and he focused it onto the sample of the colloid solution, and he looked at the microscope here, and he could essentially see particles here, and he could measure these particles. And this was something, this ultra microscope was something that was used by Jean-Baptiste Perrin to look at Brownian motion, which won him a Nobel Prize. So, Brownian motion that Perrin measured was able to give us a very good estimate of Avogadro's number, which got, and also the atomic hypothesis, which got Perrin the Nobel Prize. Zsigmondy also won the Nobel Prize in 1909. Perrin won the Nobel Prize in 1925 or 26. So, they were using the ultra microscope, and then Zsigmondy then worked on this a lot more and improved the ultra microscope. So, what you get is you have this Tyndall effect that you see in colloids, and this is because of the size of the particle. So, that is one optical property. So, this is the Tyndall effect that we have got to, and we now know where this comes from. So, colloidal optical property gives you its very nice colors, colloidal optical property. So, that is one optical property that we looked at. The next thing that we look at is some of the kinetic properties, and they come in two different kinds. So, one we have in some sense looked at. So, there is diffusion, there is Brownian motion, there is dialysis, and there is a whole sort of set of electrokinetic experiments in which we have electrophoresis, electroosmosis, and streaming potential. So, let us look at diffusion, and again we will look at the experiment that Thomas Graham did. Graham did a very interesting experiment when he was looking at diffusion in liquids. What he did was he took a vial. This did not have parchment, by the way, this is just a vial, and he took a solution and he put this into a gel. First he put it into water. So, he took this, he stuck this in and he put it into water. Well, it does not look like it shouldn't look like it is floating, but anyway he put this into water. And after some time he measured how much of this had gone into this, and this was clear illustration that there were things that were diffusing out of this, otherwise how else would you get salt from here into the air. So, there was diffusion happening. And if you remember Robert Brown, there is also this Brownian motion. So, this diffusion was then related to the temperature and things of that nature by Einstein in 1905. So, when you have colloidal particles, you have, because of their sizes, you are going to see something which is a little bit different in their appearance from what you have with normal particles. So, the other thing that happens is, and this is Robert Brown's experiment, when he took pollen grains and he put it in water and you put it into under the ultra microscope, the thing that was developed by Zsigmondy, what you could clearly see was that these particles were moving around, and this was the first illustration, clear experimental illustration of the validity of the kinetic theory of gases and liquids. And it took until 1905 before Einstein could then give a simple relationship between the diffusion constant, which is related to the size of the molecule, and the random motion that happens. How does this happen? I mean, very simply the physical picture is this. Imagine that I have a pollen grain inside a liquid, and the liquid, from your knowledge in ninth class chemistry, is made up of particles. And the kinetic theory gases says that, look, the particles that compose this material object here is undergoing random ceaseless motion. So, if you take one particle here, so this is the pollen grain, let us say that Brown is interested in, you focus your microscope in this and you follow its trajectory. When a particle, that is a molecule of the solvent in which this pollen grain is suspended, when it undergoes a collision with this, that based on the momentum that the particle had, this particle will undergo a motion. So, it undergoes random motion like this, and if you looked at an average, the position of the particle after some time will be exactly where it started off. But if you look at the root mean square displacement, that is proportional to the number of steps, that is the number of collisions that these particles take. In other words, that is the time that you have got, that you have followed that particle, and also the diffusion constant. So, this transfer, this translational diffusion Brownian due to Brownian motion is related to the diffusion constant d and the time that you followed. And through a very simple Stokes-Einstein-Stokes relationship, you can relate the diffusion constant to the size of the molecule. So, this is one kinetic property that is easily followed in colloidal particles. So, we have come across two of them now so far, one optical property and one kinetic property. The other thing that we will look at is, what did we say? We said diffusion, we looked at Brownian motion, and we look at dialysis, which is an experiment that we have already discussed when we talked about Thomas Graham. This is something that some of you might have encountered. If you have a person who has a poorly working kidney, then what they do is kidney dialysis. So, a person who has a bad kidney needs to have dialysis because the kidney, one of its functions is it works as a semi-permeable membrane. And it works as a semi-permeable membrane, and things that is not required in the body, like for example urea or creatine, things like this are put through the membrane and shunted out, and this comes out through urine. Whereas, if your kidney is not working, then the levels of urea and creatine are high in the blood. So, people who have a very poorly functioning kidney either need to have a kidney replacement, or sometimes what they do is, until, because kidney replacement is not something that happens overnight. So, you need to keep this person alive till you find a replacement, and what they do is to put you through a kidney dialysis. And what happens is, the blood that you have in your body, you take it out of your system, you put this blood in through a membrane. So, the blood goes in, this is a semi-permeable membrane. So, when I take this blood that comes out of my body, I put it through this semi-permeable membrane, urea and things of that nature come out. They permeate, dialyze, so they come out of this, whereas some of the nutrients are put back from the solution into this. And then after you come out, the blood that is now pure is put back into you. So, this is an example of dialysis, and it utilizes the same thing that Thomas Graham did. I hope you remember that experiment, right? you take something, you have a membrane and you put this here, water. So, when the concentration here, so the concentration here is concentration, let us imagine it is sodium chloride, the concentration of CnACl in this is higher than this, as a result of which the sodium chloride diffuses through the semi-permeable membrane and comes into here. This is called dialysis. In some sense, this is how your reverse osmosis machines also work. So, this is osmosis in some sense. So, people call it dialysis. So, you put this and you put in through a semi-permeable membrane, and because of this concentration gradient, it will just go from here to here. And that is exactly the principle that we use in kidney dialysis. The blood comes in, you have a semi-permeable membrane, and the concentration of urea and creatine is higher than what is there in this surrounding medium. So, the urea and creatine will flow out of the semi-permeable membrane. This, which should have been done by the kidney, is not being done well. As a result, you have to take the blood out of your system, put it through the membrane, and then put the blood back into your system. And then you can do this. You do not have to do it regularly, maybe in 2 or 3 days you go back and get your blood cleaned through a dialysis, and once you found a replacement kidney, you can have your kidney replaced. So, dialysis is another thing that one encounters when you are looking at colloids. So, the next thing that we will look at is the charges on these colloids and also their electrokinetic properties. So, if you look at, so some of the colloids, so what are the kinds of colloids? Colloids are, how are they prepared? So, let us first look at that before we come back to the charges on colloids. Colloids are of two kinds. You can preparation of colloids happen generally either through what is called condensation or through dispersion. You can understand what it means. This is called the bottom up approach, whereas this is called the top down approach. Dispersion, what do you need to do? You have a material which is big and you want to put it into a condensed phase. So, what do you need to do? You need to break it, which means that you have to disperse it. So, that is one way of doing it. You take any material which is in the solid form, let us say, or anything else, liquid droplets, big droplets, and you apply some mechanical device. So, for example, a mill, a colloidal mill for example, you take these big particles, put it into a mill, put it into a dispersion phase, and you can disperse it. That is the top down approach. The condensation approach, on the other hand, you take small molecules and you put them together. So, you have to bring them together. See this, if I have a surface like this, if I have a material like this, if I break this, I am breaking bonds here. So, if I move this, this condensed thing has higher stability than when I break it apart. So, if I looked at the Gibbs energy as a function of the separation of these two things, you will find that it goes like this. So, together, that is, when the two particles come together, because of the surface interactions, this is going to be more stable than if I had this, right. So, condensation is the natural thing that would happen. So, if you did not pay attention, then all of them will clump together. So, this is the condensation approach, and you can see various examples of condensation. If you take ferric chloride and take water and heat it to 100 degrees Celsius and add ferric chloride to it, then and maybe sometimes add a little bit of sodium hydroxide, although you do not need to, and you will quickly form a ferric hydroxide sol. So, that is an example of a condensation process. The same thing that, so this is an example of a condensation preparation of a sol. What Michael Faraday did when he did a gold sol was to take some compound of gold, typically HAuCl4, and then you reduce this. So, this is in gold is in the +4 state, and if you reduce it with the by adding a reducing agent, you will get gold in the 0 state, and this gold in the 0 state is now a colloid, and that is how Michael Faraday got this. Yes, it is true that you have to make the solution especially dust free, etc., etc., but this is all condensation process. You take sodium thiosulfate, for example, and this is a titration, a reaction that you might have done. If you take sodium thiosulfate and you add HCl to it, then automatically it undergoes a disproportionation reaction to give you sulfur 0 and sulfur dioxide, and the sulfur 0 also is a colloidal particle because it forms S8 particles. So, these are all examples of condensation procedures to give you colloids, and the exact procedure is probably something that you will look at. But in general, preparation of these colloids will require either putting together things, which is a condensation, or a dispersion where you take a material and then break it to get it into solution, into a dispersion, right. And something that you will find very often is a very good example of a colloid that is typically given is that of silver iodide. So, if you take potassium iodide and add it to silver nitrate, you are going to almost immediately get silver iodide precipitate, but if you can control it a little bit, you will get silver iodide as colloidal particles. Now, if silver nitrate happens to be in excess, if silver nitrate happens to be, so the silver colloidal particle, silver iodide colloidal particle that you have got will now is you have silver nitrate in excess here. So, the thing that will come off from the silver iodide happens to be I minus, right. So, what will happen is this surface will have a positive charge because there is too much silver here on the outside. So, the I minus will come off. On the other hand, if you added silver nitrate to potassium iodide, the reverse would happen. So, the particle that is formed has a charge. You see, there is a solubility product for silver iodide, right. The solubility product is 10 to the minus 16. So, 10 to the minus 16 is what I meant. So, if you have equal concentrations of silver and iodide, then you expect that each of these concentrations is 10 to the minus 8. But now, if the concentration of one of these is higher, then appropriately to meet the solubility product, you have to adjust the concentration of the other one. So, that is what happens. So, if this is in excess, then I minus will change. So, if there is more of silver nitrate, I minus would change. If there is more of I minus, Ag plus would change. As a result of which, and this will happen by surface dissolution. So, each of these colloidal particles is charged as a result, and because of this charge, the stability also is related to the charge that you have. How do you know that this thing is charged? If you take a U tube, so how do I know this thing is charged? Let us imagine I have a U tube here, and initially imagine that I fill water up to here. Okay? This is initial, and I fill water here. So, this is water. Now, I slowly add this silver iodide or ferric hydroxide, whatever the salt that I have made, I slowly add by the side, through the side I add silver iodide, And so, in the second stage, if you looked at it, my U tube would have my sol here. So, this is my sol and this is my silver water here. So, I have water on both arms and I have the sol here. Now, imagine that I stick two electrodes here, plus minus, and connect it to a DC voltage of 24, 25, 30 volts, something like this. So, I am applying a potential across these electrodes. I have a sol here, and because the sols are viscous, and we have seen from Thomas Graham's experiment, when I have a sol here, it does not mix with the water. So, do not get worried, you are saying that, oh, this man is making a mistake, that how is it that this does not mix? It does not mix because this is a sol. So, now if I apply a potential here, based on the charge of the particle here, you will see a movement of the sols towards one of the electrodes. If it is positive, this would move to the negative electrode, and if it is negative, it will move to the positive electrode, and this is what is called electrophoresis. Right. So, you have electrophoresis based on the charge of the sol here. When you apply a potential, you will get the sol to move from one side to another. If it is positive, it will move to the negative electrode, and if it is negative, it will move to the positive electrode. This is what is called electrophoresis, and there is a use for this. When you have a furnace, for example, and you are burning some charcoal and things like that, these will get smoke, right, and smoke, we said, is a colloidal particle. So, what you do is, before you release this smoke from industries, if you want to release this out into the atmosphere, that will cause pollution. So, what you do is, as this flue comes off from this furnace, you put in an electrode which is appropriately charged, and you raise it to the potential, and these smoke particles which contain these charged colloids, based on this electrode that you have got, will go and get attracted. And so, the glass that comes off, which you can put out into the atmosphere, is cleaner than when it came in. So, there is a very, very simple implementation of this. This is called the Cottrell precipitator, and a picture of it is there in your book. So, make a look at it, and the idea is very simple. The sol, that is the smoke that you have got, is charged. So, when you put an electrode and put a charge through this, then this thing is going to get precipitated, it is going to get attracted to the electrode, and then you can move this. So, this is one way of doing this. So, this is where you are using, but you do not need to use electrodes for all this. Because these things are charged, these colloidal particles are charged, you can then adjust the stability. The stability of these colloidal particles is also going to be dependent upon the charge. So, but this requires a little more discussion. So, what we will need to do is look at how you can stabilize these particles and what is it that leads to its stability. We have already said, so when you have two surfaces, being created, you need to do work. So, it is easy to come together. So, this is when two particles, so two colloidal particles, both of which have surfaces, and we said the state where they come together is the one which is lower in energy. So, there is a tendency for this to come together, and but when it is in a liquid solution, there is interaction between these particles and the solution that you have got, which makes a repulsion between these two particles. So, there is a repulsive part arising as these particles come together, and it is an interplay between the repulsion that comes and this thing which brings it together. This is something that we will look at in the future discussion. So, we have just started our discussion with colloids, and we have looked at a few properties. I think at this point we will close for the day. Thank you.